Welcome to Chapter 4 of this class on partial differential equations. In Chapter 3, we introduce distributions and Sobolev spaces. We're going to use them today to prove existence, uniqueness, and continuous dependence of the solution with respect to the data for a class of partial differential equations, basically elliptic PDEs. We're not going to solve the problem for every elliptic PDEs. That would be obviously an open problem today, but we will see a method that will work on a wide class of elliptic PDEs. And in this video, what we will do is explain to you what we're going to do in the next videos and basically what we're going to solve together this week. Let me start with an example here, which is this PDE. Minus u second plus cu equals f inside of the interval 0, 1. And basically at the boundary, we have u of 0 equals 0 and u of 1 equals 0 as well. That is the boundary condition. Now, c is a function given, and f is also a given function. The question is this problem well posed? In other words, do I have a solution? Is this solution unique? And is the solution continuously dependent on f? In other words, if I have a small variation on f, do I have a small variation in my solution? Obviously, the answer to this question will be it depends on f and c. So let me rephrase my problem in a different way. Can we find three normed vector spaces f, g, and e such that for all data f in that vector space f, for all function c in that vector space g, there exists a solution u in E that is basically solution to that equation, and that will satisfy this continuous dependence, in other words, such that the norm of u in E is bounded by a constant times the norm of f in f. Now, as you can see, I write UFC to insist on the fact that u will depend on f and c, but soon enough we'll drop this f and c, so it's just easier to write. Okay, now what happens in higher dimensions? We'll have minus Laplace operator u plus cu equals f, and u equals to 0 on the boundary of omega. And of course, that is, I would say, a real PDE. I mean, the one before was a PDE, but it was in dimension 1, so it's really an ODE. This one is a full-fledged PDE in high dimension, and the same question arises. I mean, do I have here a PDE that is well posed? Well, this is the kind of problems that we will address today. Actually, today we will address finding the well-posedness for these types of equation. Again, we'll actually do it on examples, but the methodology we'll give and the theorem that we will give, which is the Lax-Milgram theorem, will be applicable to a wide class of problems. All right, so before we actually tell you what we're going to do in this in the next videos, I would like to say that this problem is called a Dirichlet problem. And what is a Dirichlet problem? It's a problem, it's basically finding a function u that is governed, that is given by a partial differential equation inside of a domain, so in the interior of a domain omega, an open set, and that is taking a prescribed value on the boundary. So that is what we call a Dirichlet problem. Another definition is what we call a classical solution to a PDE. Here we have a second order PDE. We have a Laplace operator. Laplace operator, as you know, is the sum of the second derivatives of my function. So you need to have 2 degrees of differentiation to have a differentiation in a functional space. Otherwise, we're going to have to go into distribution. So the classical solution is really a solution that can be, that is classical. In other words, for this to happen, I need to have u in C2, so I can take two derivatives. Otherwise, we will have what we will call a weak or variational solution. In other words, we're going to have to multiply by a test function in order to be able to give sense to this equation. In this chapter, our goal is to establish the well-posedness of this equation. And by doing so, we will give you a general methodology that you can adapt and use on other elliptic PDEs. So let's see how this chapter is organized. In the next video, we will discuss duality in Hilbert spaces. Now, many of you are probably thinking, well, there is not really a point in doing a full video on this because we already know that the dual space to Hilbert space is that Hilbert space. Not so fast. The dual space to a Hilbert space is that Hilbert space if you consider the inner product and the norm of that Hilbert space. But if you actually take that norm and that inner product of that Hilbert space, but you choose a Hilbert space that is smaller than this, or just a Banach space which is smaller than this, then the dual space is not going to be that space. So that is something that needs to be discussed. Obviously, we're not going to discuss this in the introduction. We're going to discuss this in this section 1. That will be a video about duality in Hilbert spaces, especially what happens if I have a smaller space than the main Hilbert space. Number 2, Lax-Milgram. Lax-Milgram is really going to be the main result of this chapter. And number 3, that will be an application of the Lax-Milgram theorem, and we'll see how we can use Lax-Milgram to prove well-posedness of minus u seconds equal f, that's dimension 1, and also how we can solve, in the sense of finding, proving the well-posedness of minus Laplace u equals f in higher dimension, and we'll just choose dimension 2 for that matter. Okay, so that will be our chapter 4 about the variational formulation. So let's come with me and watch the first video on the duality in Hilbert spaces.